Okay, so let's think about graphs in polar coordinates. Remember, the polar coordinate means that you have a full coordinate system where every point is given by its angle from the x-axis and the distance from the origin. We also had a few formulas that we went over last time, which was that r is equal to square root of x squared plus y squared. Theta is equal to inverse of y over x. And then x equals to r cosine theta, y equals to r sine theta. Okay, so that's the setup. So let's start with the most obvious one, example 1. What's r equals to 1? Well, that means you're looking at points that are distance 1 away from the center. What does that give you?
Unit circle.
A unit circle. Okay. Now, let's take a slight different strategy. How would you go about writing down lines in this coordinate system? So, for example, think about y equals to x plus 2. How's that? Y equals x plus 2 is this line written in rectangular coordinate system, sometimes known as the Cartesian coordinate system. How do you change this into r and theta? Well, you can just simply plug these two in here, and that gives you the answer. So what you have is replace y by r sine theta, replace x by r cosine theta, just like that. And just like how usually you want to write down your equation in terms of y equals a function of x, in the polar coordinate system, the preference is to write down the equation as r equals to something. So we need to solve this for r, and the way you solve this for r is by subtracting the r cosine theta both sides, factor the r, like that. Okay, so you have this very weird looking formula in the polar coordinate system, which is equal to y equals x plus 2. Okay? Now that immediately makes you think, like, why on earth would you want to express a simple thing y equals x plus 2 like that? Well, as I said before, sometimes polar coordinate system allows you to do calculations in terms of integrals. Yeah. And there are cases where writing it down in polar coordinate system is easier. So let me start with something that's really hard to do it in rectangular coordinate system, which is, think about this one. R equals to, say, three cosine theta plus let's think about this example. Now that's something that we haven't done before, so we have no idea what kind of graph this is going to give you. And it's not so straightforward to change this into rectangular coordinates either. See, you can sometimes rewrite that. So for example, if I have r is square root of x squared plus y squared, right? And then cosine theta, if you solve this for cosine theta, you can replace cosine theta as x over r, which is not so helpful. Oh yeah, that's okay, yeah. It's x over r plus 3. But then you can replace this r as using this one. That's right. So that's what you get in terms of rectangular coordinate system, and that's not really helpful at all, right? Yeah. I mean, would you be able to draw this graph? Very hard, right? So instead of taking this approach, sometimes this works. Sometimes, occasionally, you get an equation where changing it like that does help, but this one doesn't help us at all. Instead, what we can do is we can make a table of r and theta. To draw this graph, we need to make a table of r and theta. And that's like, if you recall how we drew graphs in rectangular, that's what we did, right? In high school, when you learned how to draw graphs for the first time, you made a table of x and y values. So that's exactly what we have to do in order to draw this graph. So let's start from angle 0. And then there's always this question of, let's just go with pi over 2, pi, 3 pi over 2 is this much. And then if we don't know what's happening in between, we can plot more things, right? So for these, let's think about what the value of r is. So first of all, what's cosine 0? Recall the graph of cosine, right? Like that. The values of cosine at those angles I drew is 1, 0, -1, 0, and 1. This is the graph of y equals to cosine theta. So if you look at the values of the cosine, it goes from 0, 1, 0, -1, and then 0. So you just have to replace these by those values. So when theta is 0, you get 1. So you get 3 plus 3, which is 6. When theta is 90 degrees, or pi over 2, you're here is 0. So you just get 3. And when theta is pi, what do you get? When theta is pi, according to this graph, you're where? 0. Yeah, you get -1, so -1 times 3 plus 3, you get 0 as the r. And then you come back to 3 again. Okay? So let's try to draw those points, see if it makes sense. So let's just say this is 6. So this must be 3. It's 3. This length is 3, okay? And 0, okay. So when you're at angle 0, which is this ray, you are at 6. And then it goes up. Okay? As the angles go up, you can see that the value of cosine goes down, so this value shrinks. So as you go this way, it does this, right? And then the values So from 0 degrees to 180 degrees, as you rotate, the value of r just keeps shrinking and shrinking, shrinking to 0. Okay. So it at this point when it's 180 degrees, it completely hits 0. And one thing that you have to know is that I mean, we're only using 4 points, which is very crude, but if you use more points, what happens is that it's going to shrink down to 0, and then it will hit the 0 at this angle. So in other words, this line will be a tangential direction, okay? So we like that. And then the same thing is going to happen if you go the negative direction. So that's what you're going to get. And there's a name for this curve. It's called cardioid. Because if you turn this around, it looks like a heart shape, right? Not a good one, but somewhat of a heart shape. And this is something that you can see on microphones. So next time you see a microphone at a karaoke or at a church or someplace, if you have a microphone, look at what it says. And 9 times out of 10, the microphone that you're holding will be a cardioid microphone. Okay. So what's a cardioid microphone? Well, cardioid microphone is a microphone where if the microphone is held like this, and the singer's mouth is over there, okay? And directly towards to the axis of the microphone has the best sensitivity of the sound, okay? Right behind to the opposite, it will have the worst sensitivity. And if you go somewhere here or there, it will still pick up some sounds, but it will have less sensitivity. So the most popular kind of microphones are known as the cardioid microphone, whereas the next popular ones are called omni microphone. Omni microphones have sound response of a circle. In other words, at 360 degrees, it has the same response. These are used when you're recording choir or orchestra, and you see these microphones that come from the ceiling. Those are omni microphones because they need to collect sounds at an equal volume, right? But when you have a singer or somebody speaking at a podium, the microphones there are cardioid. If you actually buy these microphones, and if you look at the manual for these microphones, you open up, you will see these graphs. Okay? For cardioid microphones, they actually have this exact same graph explaining that this is the sound response of this microphone. That's how people engineered it. Okay? Now, I actually do not know why it has this explicit shape. I just think that if you have, so in general, cardioids are, so in general, if you have A cosine theta plus A, or plus or minus A, and A sine theta plus or minus A could be negative, okay? These have cardioid graph. So these are cardioids. And I think what's happening is that A, if you have a constant value, that's an omni microphone, right? But then cosine is like projecting something. So there's like some manner of projection to this central axis that you would have such a thing. Yeah, and I think they're using something like some ways to reverse the sound coming from it so that the sounds cancel. I don't know exactly why, but I'm just pointing out that anytime you buy a microphone, look at the manual, you'll see this graph. That's called cardioid.